Okay, so today we're going to be doing EE386 midterm 2 review. And so we're going to be taking off where we left off on the last one. So this one will be starting with lecture number 5. And so what we need to know is we're starting with the system function. So you probably recall the convolution where you do the input convoluted with the transfer function. So our h of n convoluted, which is our system here, h of n, convoluted with the input x of n. That can be written as the summation, and it would go from negative infinity to infinity of h of k, x of n minus k. And so when you do the discrete time Fourier transform, what you're going to get is you notice you get y e to the j omega is equal to, and instead of convolution, it becomes multiplication. So it's just h e to the j omega multiplied by x e to the j omega. But this would be using the dtft and applying the z transform on top of this. What we're going to get as a result is y of z is equal to h of z x of z. And so what we have here is we're now working in the z domain. And so a lot of times we refer to our system function. And what is our system function? Remember, our system here was h of n, and then we took the dtft, so it became capital H e to j omega, and the z transform was h of z. And so system function h of z is equal to the output y of z over the input x of z. And so what you need to know is this is oftentimes called the system function. And what we like to do a lot of times in 386 is we start with a linear constant coefficient difference equation. And you've probably seen this from Math 370A. The linear constant coefficient difference equation is written in the generalized form y of n is equal to, and then it's the negative summation from k equals 1 to capital N, a of k, y of n minus k, plus, and then we have the summation from k equals 0 to capital M, b of k, x of n minus k. The important thing to note here is just the summation of the two. The a of k is the coefficient of the y terms, the b of k is the coefficient of the x terms. And notice that we have a minus sign for this one because we brought the y terms after time step 0. So for time step 1 to capital N, we brought it over to the right-hand side because you usually have all your y terms on the left-hand side and your x terms on the right-hand side when you have an equation such as y equals mx plus b. You usually have your x terms on this side and you have your y's on this side. So we brought it over right-hand side, so that's why it's a minus here. So this linear constant coefficient difference equation, what we like to do a lot of times is you can manipulate it to get you the transfer function by taking the z transform of each of these terms. And what you're going to get as a result, when you take that z transform and you solve for the system function, it's going to be, remember, the output over the input. And it can be written in this form where we start from 0 to capital M, and it's going to be bkz of negative k all over 1 plus, and then capital N, k equals 1 to capital N, a of k, z negative k. And this would be your generalized format when you're solving for that system function. And we saw within the class, we plugged this into MATLAB in order to prove it. And so now that we talked about that, the other thing that I want to just discuss before we start getting into all the examples here is when you have your y-then equation, so when you're trying to find the response, which is given by your y(n), because this is the output, it's the response. So we're going to deal with responses in lecture 5. And there's two types of responses, the transient and the steady state response. Those are the two types you'll commonly encounter. And so when you have y(n), which is your output, which gives you your response, is equal to the summation from k equals 1 to capital N, and then it's going to be a of k, pk of n, u of n, plus, and then it's from k equals 1 to L, and then it's capital Q of k, lowercase q of k, and then n, u of n. You have to tell which one is providing the transient part of the equation and which one's providing the steady state part of the equation. And so what we look at here is we have to do a little analysis in order to determine what's the response of our output. And this is something we saw in the laboratory. So this term right here, this one is due to the system function, which remembers h of z, and it's called the natural response. The natural response is also the transient response, so I'm going to just say natural / transient response. And so what we're going to see is if our p of k here is less than 1, let me fix that real quick. For all k, what we're going to see is the natural response goes to 0. And why does it go to 0? It's because if you have a number that is a fraction here because it's less than 1, so say it's like 3/8, as n keeps increasing, it keeps getting smaller and smaller, and this will die out, this part of the equation. Where the second part, this one is going to cause the steady state response. And so what we like to do is when we talk about this part of the equation, this one is going to be due to the input signal, x of z. And so for this one, what this one is known as is the forced or steady state response. They're interchangeable. You can use one or the other because it stays there the entire time after the transient response dies out. And this one, oftentimes, what we see is if the poles fall on the unit circle, it's a sinusoid that persists for all n greater than or equal to 0. But what we notice is this term remains while this term usually decays because this part will go to 0. And so this term will just equal 0. And then only this one will remain as time goes to infinity. And now we need to have certain conditions. We talked about in this lecture causality. So causality and stability were two major ones that will be examined on. So make sure you understand it, and we'll do a bunch of examples after. But causality, what it said, in order to be causal, a linear time invariant system, so an LTI system, is causal if and only if the system function, which is h of z, so the system function, and remember, when we solve for that, it's h of z, is the exterior of a circle. And what do I mean by that? What we're going to see is when we have our region of convergence, remember when we're dealing with the z transform. And when we solve for it, we get like a pole here And when we have a pole, it makes an entire circle around it. And we're going to see that the region of convergence will fall outside of that circle. That is a causal type of signal when the region of convergence is outside of the circle. And so we have a pole which creates the circle around it because it's a unit circle. It's uniform all around it, that circular ring around that pole, the distance from the origin to that pole. And so what we're going to notice is that region of convergence will fall outside the unit circle. And then when we talk about stability, that's another major one. So stability, when we have it, it's defined as the unit circle is contained in the region of convergence of the system function h of z. So this one's pretty big. In order to have these two conditions, what we're going to see is if we had a unit circle, for example, and say the pole was given at -3/8. Well, remember that pole, when you do the absolute value, it's going to make an exact on that circle where that pole occurred, -3/8 out from each of these. What we're going to see is if the region of convergence, it includes the exterior, so that'd be the exterior here, it's going to include -1. And then +1, of course, because it's the absolute value for that region of convergence. So that's the unit circle, right? It goes -1, it goes 1 over here. It's going to be +1, so or positive j and then -j, because this is the imaginary axis, this is your real axis. And if your region of convergence here is outside the unit, outside your 3/8, it's going to include the unit circle within that region of convergence. And that's what we see here, is it's still including that unit circle outlined in blue. And so that means it is stable. So for example, here we had for our region of convergence, z was greater than 3/8. And so that's why we drew the circle around the 3/8 all from the origin. We were able to, because it's absolute value. So anywhere the distance 3/8, that pole, that's its region of convergence circle, and then everything on the exterior of that, because it's not including, it has to be greater than 3/8. And then what we see is that region of convergence shaded in yellow is going to include the unit circle outlined in blue, which the unit circle is defined as 1 unit from the origin. And so now we have these two conditions. If it's causal, it's the exterior of the circle. If it's stable, it includes the unit circle. Now, if it's causal and stable, causality and stability, what's going to happen is the region of convergence is in the form z is greater than r. So that means it's the exterior of the circle, and where our r is going to be between 0 and 1. It includes 0, but it will not include 1. The reason is, remember when we drew our pole at -3/8, the region of convergence is greater than 3/8. It's not including 3/8. So in order to include the unit circle, it must be just less than 1. So it makes sure that area of, for the region convergence will overlap with the unit circle. It's not right on the unit circle. So when we talk about R, that refers, of course, to the pole, because 3/8 was our pole here, and we made the circle all around it. And then the region of convergence was everywhere shaded outside, but not including that circle around that pole. And so here, what we notice is the region of convergence is in the form. So this means right here that it's the exterior of a circle. And here the pole must fall within 0 to 1. So that means it must be anywhere in between here from 0 all the way up to, but not including 1, so that it can include the unit circle. And so that would be for your system function, that region of convergence, h of z. And so you notice that h of z was important because it determines what the causality and stability based on its region of convergence. And so now let's do some examples applying what we learned here in order to have a good understanding behind this lecture. So the first one that we're going to go to is going to be an in-class exercise that we had. And so here we were given the input to a causal LTI system. So I'm just going to call this example. And what it tells us is the input to a causal LTI system is, and then we have x of n, which is going to be, oh, sorry. Oh, I can't see the chat box for some reason. Let me escape real quick and reopen it. Oh, this one's from the in-class example, Cato. Sorry. So this one was from 10-18. So they gave us the input to a causal LTI system, which is u of negative n minus 1 plus, and then 1/2, and then it's raised to the power of n, u of n. And so in order to solve for this one, they give us the z transform of the output of the system is, and so this is the output, so y of z, that's what we should be expecting, negative 1/2 z negative 1. And then for our poles down here, we're going to have 1 minus 1/2 is z minus 1, 1 plus z to the negative 1, okay? And so we're going to find the system function h of z. And so remember what we need to do is the system function is given by y of z over x of z, the output over the input. Well, they gave us the x of n, but it's not in the z domain. So we have to convert this first to the z domain, and then we'll solve for the system function by doing the output over the input. So in order to transfer x of n over into the z domain, what we're going to have to do is we're going to use our z transform table. And what you're going to see here is notice that the first one is u of negative n minus 1. So matching this up with the z transform table, we have u of negative n minus 1. Here, though, what we're going to see is we don't have this term in front. But don't you agree that 1 raised to any power is just 1? So like 1 to the power 1,000 is just 1. And so what we're going to notice here is our alpha, we'll just substitute in 1 for it because it's just going to be 1. But we also have a minus sign here. So we're going to have to put a minus sign on the z transform because we don't have that on ours. So what we're going to notice is we were just given u of negative n minus 1, and we had to take the z transform of that. So here for alpha, anything 1 to the power of anything is going to be 1, so it won't change our result. So we're going to substitute in for alpha 1. And then if we weren't given a minus sign in ours, so we're going to move that minus sign over to the other side for the transform because it was not included on ours. So we have to multiply by -1 here because we didn't have it on the left-hand side. And so when we take the z transform of that first part, what you're going to get for x of z, it's going to be equal to -1 all over 1 minus z to the -1. And then for the next part here, which this is alpha to the power of n, u of n, where alpha is 1/2. When we look at our z transform table, the 1/2, which is our alpha to the n, u of n, we're going to write the exact same thing here, 1 over 1 minus 1/2 z to the -1. So substituting that in, we're going to have plus 1 all over 1 minus 1/2 z to the -1. And then whenever we take the z transform, make sure that you specify the region of convergence here. And so the region of convergence, since this was the anti-causal, this was the causal signal, looking when we took the anti-causal, it was z had to be less than alpha, and we determined that the alpha was 1 for the anti-causal signal. So let me just write that right below it. Z was less than 1. We're here, the region of convergence, it was the causal part of the signal. And so the causal part, it was z has to be greater than 1/2. So this is just your region of convergence for your x to z. So you have that down. And what we're going to do is we're going to find the common denominator, and then we're going to simplify it. And so for x to z, if we're trying to find the common denominator, I'm going to do 1 minus z, -1, 1 minus 1/2 z to the -1. And then when you multiply in the numerator, this side would be multiplied by this denominator. So you get -1 minus 1/2 z -1, and then plus 1 minus z to the -1. Okay, now we have this in our numerator, and then we have our denominator here. Simplifying our numerator, what's going to happen is we're going to get -1 plus 1. That would be 0. We're going to have a positive 1/2 z to the -1 minus z to the -1. So we're going to get a minus 1/2 z to the -1 when we simplify that numerator. And then for our denominator, we're going to get 1 minus z to the -1 multiplied by 1 minus 1/2 z to the -1. What we're going to see here when we simplified it, we're going to now plug it in to our system function, which is h of z is equal to y of z over x of z. Which when we plug in, we're given our y of z up here, and we just found our simplified x of z. And so now for y of z, we're going to notice it's going to be -1/2 z to the -1 all over 1 minus 1/2 z to the -1, 1 plus z to the -1. And then in our denominator for our x of z, what we're going to have here is we're going to have the -1/2 z to the -1 all over, and then it's going to be 1 minus z to the -1 times 1 minus 1/2 z to the -1. Okay, so we have a fraction divided by a fraction. So the big thing is, notice things will cancel because this is in the numerator divided by, and then -1/2 z to the power -1. So these two will cancel. And then this is in the denominator. This fraction divided by fraction, this will move to the numerator. So we're actually going to see these terms cancel as well. And so we're going to be left with the following. This is the denominator, the bottom fraction, which will move to the numerator. So it's going to be 1 minus z to the -1 all over. And then in our denominator will be 1 plus z to the -1. And so now we have our h of z, which is great. But we need to specify the region of convergence. You always have to do that. So the region of convergence, what you're going to see is for a region of convergence, remember that deals with the poles. And so the poles here, we're going to notice when they talked in the instructions, they said input to a causal. So they specified this is a causal system. And we know causal is always exterior of the circle, correct? And so our region of convergence, Z is going to have to be greater than what we're going to notice is because they specified the input to a causal LTI system, output system, determine the system function, Z must be greater than 1. Because they specified it was causal, so it has to be the exterior of a circle. And we notice in the denominator here, when you solve for the pole, it's going to give you the result of -1, but remember the absolute value, so it's going to be actually 1. And because it was causal, it has to be greater than. So we looked at the poles of our system, and we were told that it was a causal system, so we're expecting exterior of the circle, and the pole was at -1, but taking the absolute value, it's going to be +1, because the region of convergence is in terms of the absolute value. So this is the answer that you should have received. He made an error in his calculation. Okay, now that we talked about the in-class exercise, what we have to do is the next example, we'll be focusing on another fundamental part we discussed about stability. So they give us, for this example, a causal linear shift invariant digital filter has a system function given by and remember system functions are always in the H of Z. And remember, H of Z is what we use in order to determine our causality and stability of the system. So 1 over 1 minus Z to the -1 squared, 1 minus 3/4 Z to the -1, plus 1/8 Z to the -2. Okay, so the big thing here, what you're going to see is, remember, we have to determine the where the poles lie in order to find out if it's stable or not, because they'll ask, is the system stable? And so remember, for stability, it had to include the unit circle. And for causality, it had to be the exterior. And so what we're going to notice is, let me just define that. Remember, when it's causal, it is the exterior of the circle. And remember, when it's stable, that means that it includes the unit circle. And so remember, when we define causality and stability, the region of convergence will be for Z greater than R. So for causality, where R is your pole, and the poles must all fall between 0 to 1. So it includes the unit circle when it's the exterior of that circle. So that's what we're expecting, is all of our poles, since H of Z is both causal, and we're going to determine if it's stable. So let me say, instead of since, if H of Z, because we haven't determined yet if it's stable. So if H of Z is both causal and stable, what we're going to notice is that our region of convergence must be greater than R, where R is a pole, and those poles must fall between 0 and 1. So that's what we're looking for. So we're in the poles right now. So what we're going to see right here is this pole occurs at 1. So this pole, since we already know this one right here occurs at 1, it already makes the system not stable. So right here, we can identify there is a pole at 1, because when Z is equal to 1, it's going to cause the error, because this one will be the result where the pole's 1. So already we have a pole at Z equals 1. And so it's already not stable because that pole is at 1. And remember, in order to be causal and stable, because they told us it's causal, so we know that, we're just checking if it's stable. The poles cannot include 1. They have to be between 0 and 1, including 0, but not 1. When you solve this is just the quadratic equation. So when you do the negative b, which would be your negative 3/4 plus minus square root of b squared minus 4ac, you're going to get poles at z equals 1/2 and z equals 1/4. So if they didn't have this term here and they only had that term, then it would be causal and stable because the poles would only be at 1/2 and 1/4. So they'd be in between the 0 to 1 here. So it would be fine. But since they had a pole at 1, then it was no longer stable because it did not include the unit circle, because it includes everything outside of z equals 1. And so this would be unstable. H of z is unstable since there is a pole at z equals 1. And that would be your answer. Okay, now that we talked about that, let's get to an example where we're going to be given specifically the input. So here's our next example. What's an important one? I think this one's good, improving. I want to make sure, though. We did one similar. So let me actually do the next one. Because this one, he's going to actually test you on the impulse response. So when the input to a linear time invariant system is, and then we have x of n is equal to 2u of n. So we have the input given here. The output is, and so we're going to have our y of n is going to be equal to, then it's going to be 4 1/2 to the power of n minus 3 negative 3/4 to the power of n, and then u of n. So it's going to say, find the unit sample response of the system. In the sample, remember, when you take a sample, isn't that the impulse you apply right there? So finding the impulse response is basically what this is saying. And so in order to determine the response, what we're going to have to do is we're going to have to find the z transform. We're given our x of n of both our input and output, because we're going to be solving for our h of n. That's the unit sample response or the unit impulse response. When you see this right here, this is referring to your h of n. That's the unit sample response. A lot of times we talk about the system function, which is capital H of z. That's the z transform of the unit sample or the impulse response. So oftentimes, I think in the later parts in problem, in problem 5, they called this the impulse response. It's the same thing, impulse response, unit sample response. So if you see either of those on his exam, it means the exact same thing. So we need to find a unit sample response of the system. So remember, when we're going to solve for h of z first, then we're going to take the inverse z transform in order to get h of n. So in order to find h of z, remember that h of z was equal to, and then y of z, the output over the input. And then we're going to take the inverse z transform to get our h of n from our h of z. So first we need to solve for h of z, but it's going to require 2 inputs. We need to take the z transform of each of these. So in order to find the z transform of my x of n, this was 2u of n. So looking at my z transform table here, when we have a u of n, recall that Here, this one, U of n, that looks good. The only thing is we have an alpha n, but remember we substitute in for alpha 1 because 1 raised to any power is just 1, so it doesn't change. So we're going to have 1 over 1 minus, and then substitute in for alpha 1, z to the power of -1. And then here is our region convergence for z greater than, and then remember alpha was 1. So when we solve for x of z, it's going to be equal to, and what we're going to see here is 1 over 1 minus z to the -1, using that z transform table. And the region of convergence is going to be for z greater than 1. And that makes sense because this is causal, right? It's u of n. It's for time 0 or greater. And so our region of convergence should be the exterior of the circle. Now, when we solve for our y of z, when we put this into our calculation, we're going to see that y of z is going to be equal to, looking at this first part here, we're going to notice our region convergence definitely should be causal. So it should be the exterior of this circle because of this u of n for time step 0 or greater. So looking at this, what we have here for the first one, it's looks like an alpha n u to the n, and then here we have just a constant multiplied in front, so it'd be a constant multiplied on the z transform as well. So here, if we substitute in our 1/2 for alpha, it's going to be 1 over 1 minus 1/2 z to the -1, where z is greater than 1/2. And so this is what we're going to see is, remember, that's just a constant in front for, but this is going to be your alpha to the n u of n. And so that's what you use your z transform table for. So it's going to be 1 over 1 minus alpha, which is 1/2, z to the -1. And then for the next one, we're going to see -3, and then it's going to be 1 over 1 plus 3/4 z to the -1. Just applying the same type of z transform there. And specifying your region of convergence so that you have it is the region of convergence for this part was from that z transform table, z had to be greater than 1/2. And the region of convergence here was z had to be greater than 3/4. Just taking that from the table, what it specified, because these were both the causal signals we had because it's u of n, and this was our alpha, so z has to be greater than alpha, so z is greater than 1/2, and then z is greater than alpha. Remember, it's the absolute value, so the absolute value of -3/4 is 3/4. And so, what is the area of overlap for this? If you had to specify the region of convergence for YZ, the area of overlap is going to be, well, when you draw the circles, this would be at 1/2, let's say, and then the other one was at our -3/4. But remember, both of these include the exterior. So if you're going to look at the overlap, so this would be the first one for the 1/2 one, it's the exterior of the circle. And then this one would be for the -3/4, the exterior of that circle. So the region of overlap between the two would be the exterior of the 3/4, correct? Because that's where both of the colors are. So your region of convergence, if you have these two for your YZ, it's going to be the combination of the two. So your region of convergence, it's, if you combine the two, it's going to be greater than 3/4. And so that's because you have to look at where do the two overlap when you specify for YZ. Now that we have that, we need to find our H of Z. So we found our YZ and we found our X of Z. And so that's great. But when we do that, we just want to simplify and we want to get a common denominator for Y of Z. So it makes the calculations easier because it's going to be in the fraction form for H of Z. And so, oh, let me look at the chat box. Where did the 2 go? The 2. What are you specifying, Kato? Oh, here in the 2 U of n. Let me see. H of Z. Yeah, you're correct. Sorry. Good job. You found the 2 there. Thanks. That was just the constant in front. So make sure you have the 2 there. Now, when we solve for y of z, in order to get that common denominator and make the math a little easier, what you're going to notice is in your denominator, you're going to have 1 minus 1/2 z to the negative 1 multiplied by 1 plus 3/4 z to the negative 1. That must mean in order to get common denominator, make sure you multiply the numerator here by this part and multiply the numerator here by the fraction, the denominator down here. And when you do that simplification, in order to get that common denominator, you're going to get 1 plus 9/2 z to the negative 1. And so that is your simplified, and your region of convergence for your y of z, remember, was for z greater than 3/4. That's what you had specified. So this would be your simplified y of z. Now that we have that, let's solve for h of z. And so remember, it's y of z over x of z. And so for our y of z, what we solve for here is it's 1 plus 9/2 z to the negative 1. 9/2 z to the... And then it's all over. And then what's under there is going to be your 1 minus 1/2 z to the negative 1 multiplied by, and then 1 plus 3/4 z to the negative 1 all over, and then your x of z. And your x of z here is going to be given by 2 over 1 minus z to the negative 1. Okay. Now that we have that written out, we're going to have to simplify. And so when we have to simplify here, what we're going to see is, are there going to be any terms that cancel? And so when we do the simplification here, sadly, there's no 1 minus z to negative 1 anywhere. But we can rewrite it so it looks at least cleaner. So your h of z is going to equal, this will stay in the numerator, your 1 plus 9/2 z to the negative 1. Remember, fraction divided by fraction, denominator or bottom fraction moves to the top. So it's going to be 1 minus z to negative 1 all over. And then this would be 1 minus 1/2 z to the negative 1 multiplied by 1 plus 3/4 z to the negative 1. And then what about that 2 in the denominator? We're just going to put it up here. So it's 1/2 in our numerator. And so that's what we have here. And so reason I put the 1/2, I put the 2 and moved it to numerator, so it's just 1/2. It's because we're solving for the poles down here, so I don't want to accidentally confuse it when I use partial fraction decomposition. Now that we have that, what we're going to do is notice the power of the numerator versus the power of the denominator. And the power of the numerator is going to be z to the negative 2, and the power of the denominator is going to be z to negative 2. So it's technically a proper because the powers are the same. And so since it's a proper fraction, we can use partial fraction expansion. We don't need to do the long division because the power of the numerator and denominator will both be the same because there's no extra z term. So it's going to be z to negative 2 over z negative 2. So for partial fraction expansion, what you're going to do is you're going to multiply. My technique is a little different from what the instructor did. I find mine way easier. You're going to multiply the numerator denominator by z to the power of, and then here we saw that the power of 2 was common. That was the highest power of z we had. And so when you multiply the numerator and denominator by z to the power of 2, what you're going to get is, okay, remember, z to the power 2, can't I multiply this one by z to the power 1, and I'll multiply this one by z to the power of 1? I'll just multiply each one inside here, so it's easier. It gets rid of the z to negative 1 for each of these. Instead of just multiplying z to the power 2 only to one of them, I'm going to multiply z to the power 1 to this one and this one. And so I will get z plus 9/2, and then z minus, and then this would be 1, of course. And then what we're going to have in our denominator is I'm going to do the same exact technique. I'm going to distribute 1z to this term and distribute 1z to this term instead of distributing all the z to the power 2 only to one term. So this will become z minus 1/2 z plus 3/4. And so now it's just written in terms of all positive, z to the positive power. It's not written in z to -1, so it looks a lot cleaner. And now that we have it in this format, after you multiply numerator and denominator by z to the power of the highest power, which is 2, we're going to divide by z. And so you're going to get your h of z divided by z is going to be equal to 1/2 z plus 9/2 z minus 1. And then when I divide by z, I make it easy and I just put z in the denominator. And then z minus 1/2 z plus 3/4. And then what you do after is you solve using partial fraction expansion. And so here we're going to have 3 terms. We're going to have a over z plus b over z minus 1/2 plus c over z plus 3/4. Okay? Because we have 3 terms in our denominators, we're going to have to solve for 3 terms up here. And so in order to solve for a, you're going to have a equal to, you're going to multiply by z, h of z over z. And then remember, in order to cancel it out, z must be equal to 0. You're going to substitute that in for z. So what you're going to get here is if you multiply this, what we have here by z, you're going to get 1/2. And then substitute in for z 0, so it's going to be 0 plus 9/2, so just 9/2. And then 0 minus 1 is going to be -1 all over 0 minus 1/2 is -1/2, and then 0 plus 3/4 is 3/4. Okay, when you're going to plug that into your calculator, what you're going to get as a result is going to be 6. Okay, so we got our first term. Now let's solve for b. Our b is going to be equal to, and then we're going to multiply by z minus 1/2 h of z all over z. And then substitute in for z, what will make this denominator cancel? Z equal to 1/2. And so that's going to be equal to, and then it's going to be 1/2 times, and then here 1/2 plus 9/2, that's going to be 10/2, which is 5. And then what we're going to have here is 1/2 minus 1, which is going to be -1/2. And then in our denominator, we're going to have 1/2. Remember, this term cancels because you multiply by it. And then we're going to have 1/2 plus 3/4. So that's going to be 5/4. When you plug that into your calculator, you're going to get -2. And then when you solve for your z, you're going to multiply this entire thing by z plus 3/4. And then you're going to do, so multiply by that entire thing, substitute in for z. It's going to equal -3/4. So that denominator will cancel. And then you're going to have 1/2 -3/4 plus 9/2. So when we're going to do that into your calculator, -3/4 plus 9/2. And then -3/4 minus 1, what you're going to get is -7/4. Then in your denominator here, you're going to have -3/4. And then you're going to have -3/4 minus 1/2. And when you plug that into your calculator, you do the division, you're going to get -7/2. Okay, now that we talked about that, so your h of z all over z, plugging in for what we saw for a, b, and c, is going to be equal to 6 over z plus, and then we're going to have -2 over z minus 1/2 plus, and then here for c, it's going to be -7/2 all over z plus 3/4. Okay, so we got our h of z over z. The next step in partial fraction expansion is to multiply everything by z. So you just get it in terms of your h of z now. So h of z multiplying everything by z, you're going to get 6z over z plus -2z over z minus 1/2. And then plus -7/2 z all over z plus 3/4. Okay, now that we have that, what we're going to do is the next step in partial fraction expansion is divide by the largest power of z. So what we're going to notice is our largest power z is going to be our z to the power of 1. So if we divide this whole thing by the largest power z, we're going to notice that we're going to get the result. Well, this one is, of course, 6 because we just simplify z divided by z. But here where we divide by largest power z, it's z to the power of 1. That's the largest power z in this entire thing. So it's going to be minus and then R2 all over. And then when you do that z to the power of 1, you're going to get 1 minus z. I'm sorry, it'd be the 1/2 in front here. So 1/2. And then z to the power of -1. Plus, and then here, what we're going to have is it's going to be our -7/2, and then all over divided by largest power z, which was z to the power of 1. You're going to get 1, and then plus 3/4 z to the -1. Here, that's what we have by dividing by the largest power z. And then we're going to use the z transform table now. So remember, your z transform table is going to be given here. And so we have 6. Doing that backwards, you're going to get 6 delta n. So it's going to be 6 delta n. And then here you're going to have, well, this is -2 over 1 minus 1/2 z -1. What you guys for those specifically for our system, is this causal or anti-causal? You should be questioning these poles here when you're taking the z transform, because you want to know which one is the proper z transform to take. There's 2 types. We can either do the one that's for causal and one that's for anti-causal, and that will give us a different result for our answer. Well, when it said this, what we determined basically was looking at these poles. So we have a 1/2 and a 3/4. Okay, now I'm looking at my region of convergence for my YZ, and didn't I have a 3/4 and it was causal there? And for my 1/2, it was causal as well when we looked at those parts individually. So because it was causal, looking from our YZ, our response, we're going to treat these as causal signals as well, because we're just using the region of convergence from our YZ, which determines the region of convergence for h of z, because yz is a factor of it. So these will be treated as causal signals when we do the inverse z transform to get our h of n, our impulse response. So this would be -2, and then this would be 1/2 n, and then u of n, and then minus, and then we're going to have 7/2. And then this would be inside here, -3/4, and then to the power of n, u of n. And so this was taken doing the inverse z transform here, of course, where we had specifically our causal signal. So we treated it as this case up here. We did not treat it as the one before because of that region of convergence of the y of z. And remember, h of z is taken from the region of convergence from y of z and x of z. And so when we did the inverse z transform, we wrote it in this notation. And then we can simplify this by doing our 6 delta n. And then what we're going to have here is our minus, and then we're going to have our 2 1/2 to the power of n plus 7/2 -3/4 to the power of n, and then u of n. So the big thing here, when you got your impulse response, so that's your answer right here, that's the final one, you need to recall that when you're trying to find the impulse response, that's your h of n. And so remember, in order to find h of n, you need to find h of z. So you need to take the z transform of your output and z transform of the input, get your h of z. And then once you get your h of z, you do the inverse z transform. So in order to find our h of z, we had to do partial fraction decomposition. And the rules of partial fraction decomposition, if you forgot just to have them down, so I'm going to just box our answer here so we don't confuse it with below. Since the power of z in the numerator matched the power to z in denominator is both z to the power -2, it was a rational function, so we could use partial fraction decomposition. Or partial fraction expansion, they like to call it. Either one works, whichever one you prefer. So in this, you multiply the numerator and denominator by z to the largest power. And so remember, our z to largest power z was to the power of 2 in here. So is z to -2, but you multiply by largest power, of course, to cancel the negatives and turn it into positives. So we multiplied by z to the power of 2. The next step was divide by z. So you get h of z all over z, which we did here. We divided by z and we put it in the denominator to make it easier. So we would get just all of our results. We wouldn't get a weird -1 over z or something because we divide by z. And so the third step was that we solved for a, b, and c. And then the fourth step was we multiplied back by z. And then the fifth step is you divide by the largest power of z. And remember, power of z, divide by, it's the secret trick of dividing by the power of 1, really, because we divided this whole expression here by z to the power of 1 because that was our largest. Oh, sorry, wait, wrong one I applied it to. Meant to apply it to the one below. Here, because we multiplied by z in this step in order to get our h of z, we divide by the largest power of z, so we divided by the secret power 1, largest power of z was 1, so divide by z over z, which is technically 1, so you divide the numerator by z, divide denominator by z. Did that here in order to get the result here. Then our sixth step was we use the inverse z transform table. Z transform from the table. And then remember, when you're taking the inverse Z transform, watch out for is it causal or anti-causal. Okay, so that's pretty much how you would find the impulse response. So that will help you on one of your questions. That's just a good example. So now that we found that, I want to do another one here where we're going to... This one's a good one. It sort of deals with the linear constant coefficient difference equation and how we solve for problems like that one. And so I think it's good to get some practice with this one because it will definitely come in handy. So for this example, it specifies that a causal LTI system is characterized by the difference equation. So that's in, remember, if they're saying difference equation, linear constant coefficient difference equation, that should be popping up in your mind. And then here they have y of n is equal to 1/4, and then it's going to be y of n minus 1 plus 1/8, and then we're going to have y of n minus 2 plus x of n minus x of n minus 1. Okay, so they gave us this and they said find the system function. Remember, system functions always h of z, as we specified from the start, and the unit sample response. Remember, unit sample response or unit impulse response are the same thing. It's lowercase h of n. So that should be a key word you're looking for when you see this. Okay, when I see system function h of z, that means I need to find my yz, my x of z. So here, when I'm given this equation here, I need to transform it into the z transform. So I'm going to have my y of z is equal to, And then remember from your Z transform here, when you take the Z transform, let me see, do I have it here? Yes, I do, up here. Okay. So when we plug in specifically our x of n, well, right here taking Z transform, this would be our y then. 1/4, and then it'd be y of n minus 1. So it'd be Z to the power of then we have our -1 here, of course. And so when we do the Z transform of this, what we're going to get as a result, the 1/4, it's the constant that just comes out. Then it's going to be Z to the power -1, remember, and then it's going to be our capital Y of Z. And then for next one, it's going to be that constant 1/8 comes out, Z to the power of -2, because that's the n0 here, and then Y to the power of Z, and then plus Z transform of x of n is just capital X of Z, and then minus, and then this would be our Z to the -1 X of Z, because the time shift here is just n0 is equal to 1. And so it's Z to -n0, so -1 X of Z. And now that we have that, let's group all of our YZ terms together and all of our XZ terms together. And so moving these over to the left-hand side, I'm going to get Y of Z, and then 1 minus 1/4 Z to the -1 minus 1/8 Z to the -2, and then equal to, and then it's going to be X of Z, and then it's going to be 1 minus Z to the -1. Okay, I got that, and now I need to solve for H of Z. Remember, H of Z is YZ over X of Z, and so what we're going to have here for our Y of Z over X of Z is when you solve for this, for your H of Z, remember, that's what we're interested in finding, so remember, that's just YZ divided by X of Z. When you move this over this side equation, divide by that, you're going to get 1 minus Z to -1 in the numerator. And then in your denominator, you're going to get the following. 1 minus 1/4 Z to -1 minus 1/8 Z to the -2. Okay, so we got that now. And now solving specifically, what we like to do is we like to have in our denominator those what do you call it? Our when we solve for Z, we like to have our poles written in the two binomial terms rather than having our quadratic equation here. And so when you find specifically when you do the quadratic of this equation, you're going to get 1 minus Z to -1 all over. And then in the denominator, it's going to be 1 minus 1/2 Z to the -1, and then 1 plus 1/4 Z to -1. And so that's the same result. If you do the multiplication in the two in denominator, you're going to get the same. It's just using the quadratic equation to solve for these two. And so now that we specified that specifically, we're going to have to solve this. Let me see, someone said something. Where did the one come from for Y of Z? The one for Y of Z. Oh, that's because this is just multiplied by 1, right? And so when you move this left-hand side, it's going to be 1 and then minus 1/4 minus 1/8, because the 1 accounts for this term. And so if you move this over all over left-hand side, it'd be 1 minus 1/4 plus 1/8 all multiplied by our YZ. So it's just from this term over here, Cato. And so now it says this is a causal system in the beginning. Notice that says causal system. So since it says causal system, our system function is given by H of Z. So that must mean that these two are written in terms of causal for a region of convergence. And our region of convergence then here would be either Z is greater than 1/2 and Z is greater than 1/4. And so combining these two conditions, the area of overlap for a region of convergence would be Z is greater than 1/2. And so that's what we specified from before in the previous example, how we got those. Now that we got it and we found the area of shared overlap, so we got the final region of convergence for our H of Z, we're going to have to solve for this specifically in order to get our h of n. So we need to use partial fraction expansion. Notice that the power z in the denominator is greater than the power z in the numerator, so we don't need to use long division since the power of the denominator is greater than power in numerator. So we can just go straight to partial fraction decomposition. So remember with partial fraction decomposition, you're going to multiply your numerator and denominator by z to the power of n. And so when we're looking at this, the highest power of z is z to the power of 2. And so when I'm writing my h of z, if I multiply the numerator denominator by z to the power of 2, I'm going to get z to the power of 2. And then here, we're going to have minus z all over. Then our denominator, we're going to distribute one the z's here and one here. So we're going to get z and then minus 1/2. And then here we're going to get z plus 1/4. And so that was just multiplying by the highest power z, because highest power z in denominator was z to -2. So multiply by z to 2 over z2. Z2 in the numerator is going to be z2 minus, and then here we're going to get z. And then distribute for z2 in denominator, distribute one z here and one z here. So we get a cleaner expression. Now that we did that, we need to divide by z. That's the next step in the partial fraction expansion from that list I gave you guys. And so divide by power z. In my numerator, I notice if I just divide by z, I'm going to get z minus 1, and then z minus 1/2 here, and then z plus 1/4, because I just divide the numerator by z, so it came out simpler. Then using your partial fraction decomposition, this would be a over z minus 1/2 plus b over z plus 1/4. Now that we have that, in order to solve for this, a is going to equal, and then it's going to be z minus 1/2. H is z all over z. Substituting in for z, it's going to be equal to 1/2. And so what we're going to notice here, it's going to be 1/2 minus 1 all over, and then 1/2 plus 1/4. That's going to be equal to 1/2 minus 1, what we're going to get as a result, 0.5 minus 1 divided by, and then 0.5 plus 1/4, you're going to get -2/3. Okay, and then when you solve for your b, you're going to do z plus 1/4, h of z all over z, and then for z is equal to -1/4. So that's going to be equal to, when you multiply this by z plus 1/4, you're going to get your -1/4 minus 1 all over, and then you're going to get -1/4 minus 1/2. And now when you plug that into your calculator, what you're going to get as your result, it's going to be 5/3. Okay, so now we got our a and our b terms that we solved for. The next step in that partial fraction expansion is, now that we can write our h of z over z as equal to, substituting for your a, you get -2/3 all over z minus 1/2, and then plus 5/3 all over z plus 1/4. Now that you got it written in these two, you're going to multiply by z, so you just get your h of z is equal to -2/3, and then multiply by z in the numerator, z minus 1/2, and then multiply by z here, of course, as well, so plus 5/3 z all over z plus 1/4. Now that we got that, we're going to have to divide by the largest power of z in our numerator and denominator. Remember, it's the secret trick of divide by 1. So it's divide by z all over z. That's going to give us -2/3, and then it's going to be 1 minus 1/2 z minus 1. And then plus 5/3, and then it's going to be 1 plus 1/4 z to the minus 1. So that's going to be your h of z still, because it's divided by 1, which is the same thing. So it doesn't affect this at all. It's just to put it in terms of use for the Z transform table because the Z transform table is written in this format. And so we just converted it so it's easier to take the inverse Z transform. Now, remember, this was a causal LTI system here. So because it was causal, notice that my poles here 1/2 and 1/4, same thing right here, we had it causal. So when we take the inverse Z transform, we're going to look at the causal condition, not the anti-causal condition, the causal one up here. So taking the inverse Z transform of this, we're going to get h of n is going to be equal to, and then we're going to have -2/3, and then it's going to be 1/2 to the n u of n plus 5/3, and then it's going to be -1/4 n, and then u of n. Okay, now that we have that, I'm gonna u of n is common to both terms, so the final answer will be the following: 1/2 and then n, and then plus 5/3, and then -1/4 to the power of n, and then the whole thing multiplied by u of n for simplification purposes. So that would be how you would find specifically your system function h of z, which we got right here. So this would be your answer for your h of z. If they asked for it, this would be the answer. And the region of convergence you would specify would be right here, z greater than 1/2. So that would be what you got for your h of z. For h of n, the unit impulse response, it would be the following. That would be your answer. And so now that we got that, the next example that I think is important was, let me look here. Is the system stable? We covered that. Given the system. And okay, the last one I think we should focus on was this one. It was a little different, but I think it was really helpful, and I think a lot of people overlooked it. In order to understand how poles and zeros work. So it says consider an LTI discrete time system whose pole 0 pattern is, and then here they're going to give you the pole 0 plot. So they're going to remember your imaginary axis is always on the y-axis, and your real axis is always going to be on the x-axis. And so at -0.5, there's a pole. At 1, there's a 0. And then at 2, there's a pole. And then at -3, there's a pole. Okay, so it says determine the system function in its region of convergence if the system is known to be stable. So that's the first part. Determine the system function. Remember, system function's always given by h of z. And its region of convergence if the system is known to be stable. Okay, so we know the system is stable, which is nice, because what they specified for us, but we need to determine the system function. So remember, our zeros are in the numerator and our poles are in the denominator. So when we write our h of z, it's going to be z and then minus, well, where's our poles? 1. And then now we need to write our zeros in the denominator. Our first one, looking from left to right, it's going to be z plus 3, z plus 1/2, and then z plus 2. Sorry, minus 2. My bad. Because remember, when you plug in -3, this cancels. When you plug in -0.5, this would cancel. When you plug in 2, it would give you the divide by 0 error. And so that's why we write it in this format. Because remember, your zeros make numerator 0, the denominator, your poles make it 0, and so then it'd be divided by 0 error for your poles. So now that we have this, we need to solve specifically, they want our h of z in order to solve for it. using the partial fraction expansion, so we can write it out in summation of the three different ones. So why can we use partial fraction expansion? Because the denominator here is greater z to the power 3 when you distribute all this. Your power z numerator z to the power 1. So we can use partial fraction expansion. We don't have to do long division because this is a proper rational function. And so when we do the partial fraction expansion, it's going to be a over z plus 3 plus b all over z plus 1/2 plus c all over z minus 2. And if you recall specifically, when you did this partial fraction expansion, what you're going to get using the same techniques as we had before, in the end, your h of z is going to equal 6/5 all over z plus 1/2, and then minus 8 over 25, and then z plus 3 plus 2 over 25, and then z minus 2. And so that's what you're going to get for your h of z in the end. So that would be the system function. You can either write it like this is totally fine, like this is correct, or you can do the partial fraction expansion just to simplify it and write it. If he asks in order to write it in terms, these would be the three terms you would have compared to just writing it. He should be fine with this format though. So then the next one for part B, this one says for stability, I think it was draw the pole zero plot, what you're gonna have, but you wanted to determine where it was causal and where it was stable. So remember, for stability, the region of convergence includes the unit circle. But for causality, the region of convergence, so causality, is going to should be remember it's the exterior, so it should be the right side or exterior, I could say, of the rightmost pole. So when we draw the pole zero plot, when we make those circles around it, we're going to look at each region specifically. So remember we had a pole at negative 0.5. We don't take into account, though, R1 because when we determine the region of convergence, correct, we only look at our poles, what's in the denominator. We do not look at what's in the numerator. So in my plot here, I'm just going to plot my poles. Then I had one at 2, and then I had one at negative 3, something like that. And so when we have our negative 0.5 pole here, if we make our circle around it specifically, what we're going to see is it's going to be like this. Then when we have our negative 2, sorry, my circle is going to look more elliptical because, oh wait, let me see. Maybe I can draw it closer. Let me draw these a little more closer. Here we had 2, and then let me just draw this like negative 3. Okay, then for R2, if we draw a circle around that one, it's going to look like the following. And then when we have our 3, it's going to be an even larger circle. It's going to be like this. Because remember, it's the absolute value, so it's anywhere around there. So you draw your 3 circles around your negative 0.5. And remember, you're reaching convergence. It's the absolute value. So any point of 0.5 distance out from the origin, it will be fine. 2, it makes that circle around it, in 3 as well, because when you do your region of convergence, you have to remember it's the absolute value. So it's any point that's that same distance away from the origin, because the absolute value is going to give you your distance. Okay. Now that we had that on our plots, what we're going to see is the possible region of convergences. So looking at our first region of convergence, what we're going to have here, let me highlight it so it's easier to tell, is for the first one, we can have the region of convergence fall within here. So that would be z is less than 0.5, which that is, if z is less than 0.5, that's the interior of a circle. So it would be anti-causal. And when we're looking at this one in particular, that one would not include the unit circle. So it would be unstable. So it'd be unstable and anti-causal because it's the interior of a circle. For the next one, the next possibility for a region of convergence is between 0.5 to 2. So here we go. This is the next area where it could possibly converge, which would be between 0.5 z to 2. So this one, it does include the unit circle, which is at z equals 1, so it's stable. But it's not the interior of a circle because it doesn't go down to 0, but it's not the exterior. It doesn't go to infinity. So I'm going to call it non-causal. It's neither anti-causal or causal because this part is anti-causal and this part's causal, but it doesn't hit 0 and it doesn't go to infinity, so it is non-causal. The next one we can have here is between -2 to 3. So this would be the last region of convergence. Sorry, the second to last region of convergence we're looking at. So it could be between 2 to 3. So this one here, it is going to be, it doesn't include the unit circle, so it's unstable. However, it is non-causal because it's the exact same thing. It doesn't go to infinity and it doesn't include 0. It's not the interior or exterior of the circle. And your last possibility here would be outside of z equals 3, which is your last, the rightmost pole. And so for z equals 3, what we're going to see here is it's everything outside. So it's going to be the exterior here. Okay, so then that last one here for when z is greater than 3, this one's going to be unstable. It does not include the unit circle, and it's going to be causal, however, because it does include the exterior, so as it goes to infinity. So those would be the possible region of convergences. I think this example is really good for just showing how those region convergence, how they're stable and causal, and tying in how to get your system function from that plot. So that will finish off lecture number 5. We're going to pause for 3 minutes real quick, and then we'll come back. So okay, now we're going to get into lecture 6. So this will be chapter 6 of the textbook. And we're going to go through basically the rest of the things you need to know, the discrete Fourier transform and the inverse discrete Fourier transform, and how to perform those operations. And so this will be focusing on our lecture 6, just doing a mini recap of the theory, and then we're going to do examples afterwards, but we have to understand the formulas that we should be aware of. And so the big one for this discrete Fourier transform, it's x of k is equal to, and then it's the summation from n equals 0 to capital N minus 1. And then it's going to be x of n e to the negative j 2 pi k lowercase n all over capital N. And this is going to be for k equal to 0, 1, 2, ... all the way to n minus 1. And then our next one, the inverse discrete Fourier transform, we're going to have our x of n is going to equal 1 over capital N. And then it's going to be n minus 1 summation from n equals 0 to n minus 1, x of k e to the j 2 pi k n all over capital N. And then it's going to be from n equals 0, 1, 2, all the way up to n minus 1. Okay, so we have these two, the discrete Fourier transform and the inverse discrete Fourier transform. And we need to build an intuition of this. So the discrete Fourier transform, just having a little understanding of what it does, it's basically a representation of the signal that we have x of n by taking samples of its spectrum. And so it basically repeats it. It like repeats this every n samples. So it repeats your signal every n samples. So it's like a repetition sort of. That's what we'll notice. There's a long derivation for it, but getting into the point, this can also be represented, our book and also the teacher, when he talks about use the DFT to perform linear transformation. So the DFT as a linear transformation, this was one test topic he was talking about. So when he refers to linear transformation, he writes the DFT in terms of x of k is equal to n minus 1, starts from n equals 0 to n minus 1, lowercase x of n, and then it's capital W, n, and then k to the n, and it's going to be from k equals 0, 1, 2, all the way to n minus 1, and then lowercase x of n, so this is the inverse discrete Fourier transform, is going to equal 1 over capital N, and it's going to start from k equals 0 to n minus 1, and then it's going to be x of k, and then it's going to be capital W, n, and then k, negative k then. And then it's going to be from n equals 0, 1, 2, all the way up to n minus 1. Okay, so we got those two. And the big thing here, notice that, let me make sure that minus sign sticks out. Instead of e to the power, he just replaces it with capital W. So here we had these e to the power of, he just replaced it with capital W. And he says capital WN is going to equal e to the negative j 2 pi all over capital N. And so literally the only thing missing here is times k and then lowercase n. And so that's why we still write it up here, times k lowercase n. So he literally just substituted in, he made a substitution for this in order to perform linear transformation. And so when he talks about linear transformation, the big thing that you need to know on this one is that in order to solve for it, you have to do the technique where you're going to have your x of k is going to be equal to, so let me write this out to make sure I give you guys the correct response. He says in the notes, x of n is going to be equal to wn times, and then lowercase x of n. And so what are these all representing? Basically, what you're going to have is you're going to have your lowercase x of n is going to equal, and then you'll be given a vector of values usually. So it's like 0, it'd be x of 0, of course, the first index, x of 1, and then it's going to go all the way up to x, and then lower capital N, and then minus 1, because capital N is the length of the vector, but because you start at index 0, you have to minus 1, so it doesn't accidentally go out of the proper indexing. And then you're going to have your capital WN. So your capital WN is going to equal. This is going to be a matrix of values. And so the matrix of values that you're going to oftentimes see here is given by 1, 1, 1, and then dot, dot, dot. And then the last one will have 1 here. So it's 1s for the first column, and for the first row here, it's going to go all the way up to 1, 1, and then here we go. So this would be the format, and then this would be WN, and then WN2, and then this would be WN2. Notice that the diagonals, then we have WN4. So diagonals here were the same. And then we have WN, and then we're going to have n minus 1, then we're going to have wn, then we're going to have 2n minus 1. So what are these specifically? You're going to see that this would be position 0, 0, and then this would be position 1, 0, because it's in going to be your row 0, but column 1. And then so on and so forth. And that's what determines the values. We'll do an example with this so you get a good representation, because now it's just sounding all like numbers probably. And then there'd be like a dot, 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 and then dot, dot, dot. And then in this last one here, we'd have wn, n minus 1, and then we'd have n minus 1. And so this is just taken from what he gave us in the book, but we're going to apply it to a practical example, so we'll know how to actually apply it. This is just all the theory right now, so it just sounds like a bunch of info just getting thrown at you. So the big thing is, when you have to do this vector multiplication of your lowercase x of n, and then you're going to have your capital wn multiplied by, when you have matrix multiplication, the big thing to watch out for is if they specify that this is an n by 1 matrix, this one must match your n. And remember, your wn, it is a symmetrical matrix, so it's going to have the same rows, the same columns. And so it's going to be capital N by n. So what we're going to see here is when we apply it to an actual practical example, this matrix method will help us in order to use the linear transformation technique. So I think this is a good place just to start with the actual example so we get some background behind what we're doing. So for this example, they say compute the DFT of the 4-point sequence. And so for the sequence, they gave us x of n is equal to. And then within the sequence, it was 0, 1, 2, 3. And this would be the linear transformation technique. So, you know, if he asks you on the exam. And so we have to find out our x of n. So right here, this is your x, lowercase x, capital N. And so we know that, but we need to find our wn. But remember, our wn is multiplied by our x of n in order to produce our result of capital X of n. So this matrix, though, right here is going to be how many? It's 1, 2, 3, 4 rows, and it's 1 column. So it's a 4 by 1 matrix. And so our capital WN, that matrix needs to be a 4 by 4 because the inners must match within your matrix technique. This must match with this one. And so this must be a symmetrical matrix. So number of rows must equal number of columns. So it must be a 4 by 4. And so now that we have that, we know that our n here will be 4. So when we set up our W4 now, W4 is going to equal, and so that's going to be 4 rows by 4 columns. And so for the first one, it's going to be W4 to the power 0. For the next one, it's going to be W4, and then it's going to be to the power 0, and then W4 power 0, W4 power 0. For the next row, it's going to be W4 power 0, W4, and then it's going to be power 1, W4 power 2, and then W4 power 3. And you're probably wondering, how do I know to write these? Look right here, row 0 times column 0. 0 by 0 is 0. Here, row 0 times column 1. 0 times 1 is 0. Here, row 0, column 2. 0 times 2 is 0. And then for the next one, row 1, column 0. 1 times 0 is 0. Row 1, column 1. 1 by 1 is 1. Row 1, column 2. 1 by 2 is 2. Row 1, column 3. 1 by 3 is 3. That's how I'm determining those. So just know it's just the row times the column will give you that. Remember, you start at row 0 and column 0 within your matrix. And so this would be W4, 0, W4, and then 2, W4, and then 4, W4, and then 6. Then you're going to have your W4, 0, W4, 3, W4, 6, W4, 9. Okay. Now that we have that, we have to determine the values of this matrix. So notice that the ones that are similar, we have W4 to the power 0, W4 power 1, W4 power 2, W4 power 3, W4 to the power 6, and W4 power 9. Okay, so in order to solve for these, when we do W4 to the power 0, remember, in our notes, we had this written as specifically, we're going to have our E to the negative J 2 pi, and then it's going to be our, let me see, what's a good way of putting this? It will be 0 over 4. Yeah, okay, so then it would be N over capital N. Substituting in specifically, we know this Rn, we're going to start at 0, right? Because this is the 0th element. And so it's going to be e to the negative j 2 pi times 0 all over. And then our capital N we determined was 4 because that is going to be the length of your matrix. It's a 4 by 4. Capital N is 4 because this is W4. So capital N is 4. But remember, e to the power 0 is just going to be 1. And so that's why for all these to the power of 0, it's just going to be 1, 1, 1, 1, 1, 1. And then for the next one, when we have W4 to the power 1, it's going to be e to the negative j 2 pi. And then what we're going to see here for our lowercase n, what should we plug in? It's going to be 1 here. Because remember, the n was given by us. Specifically, where was it? I think I wrote it in here. Then will be given by the number up here. So it's going to be 1 all over 4, which is going to be e to the negative j. And then this would be pi over 2 if you simplify it, which is going to be cosine of pi over 2 minus j sine pi over 2, which it's just going to equal negative j. Okay. Now we need to do W4 of 2, which is going to be e to the negative j 2 pi. Then your n, your lowercase n, will be 2. So this would be 2 all over 4, which is going to equal e to the negative j pi. So that's going to be cosine of pi minus j sine of pi, which is going to be negative 1. Okay. And then you keep doing that. So you plug in for your lowercase n, just whatever up here. It's 1, 2, and then etc. And then you'd solve for all them. So your W4 matrix, what you're going to get at the very end is for your W4, it's going to equal the following matrix. Once you solve for this, it's going to be 1, 1, 1, 1, 1, 1, 1, 1. Then you're going to have negative j, 1, sorry, negative 1. And then you're going to get j, negative 1, 1, negative 1, j, negative 1, negative j, okay? Then you're going to have your x of 4, which you had specifically already, it was given to you. It's going to be 0, 1, 2, 3, okay? Now you're going to do, remember, in order to solve for capital X of 4, that'd be the discrete for your transform. You're now working with capital X, no longer lowercase x. And that's going to be equal to W4 multiplied by, and then lowercase x of 4. And so when you do matrix, remember, this was 4 by 4 multiplied by 4 by 1. The inners match, so it is valid matrix multiplication. You're going to, I'm going to do an example. So the first, let me see, what would be a good one? Yeah, the first row here is going to be multiplied by the column here. And so what you're going to get for the first one is the following. So 1 times 0, 0. 1 times this would be 1. 1 times 2 would be 2. 1 times 3 is 3. So as you go to the right, you go downwards. Then for the next row, you're going to get the following. So when you go this one, you're going to multiply by that column. And so you're going to get 0 times 1 is 0. Then you're going to get negative j times 1 is negative j. The negative 1 times 2 is negative 2. You're going to get j times 3. So you're going to get j3. Then you're going to go into the next one. So you're going to get 0, negative 1. You're going to get 2. Then you're going to get negative 3. Then last one, you're going to get 0, you're going to get j, you're going to get negative 2, and you're going to get negative j3. Okay, now that you have those, you have to sum each row together. And so then you'll sum it. And so you'll go from left to right. So it's going to be the summation here, summation here, summation here, summation here. Okay, so then you'll sum them together. So you'll add 0 plus 1 plus 2 plus 3. That's going to be 6. And then for next one, you're going to do negative j and then multiply by. Then here we're going to get minus 2 plus j3. So this is going to give you negative 2 plus 2j. And then you're going to get negative 1 plus 2 is positive 1 minus 3. And so that'd be negative 2. And then last one, you get negative 2 minus 2j. And that would be your answer, specifically for your x of 4 vector that you solve for. So capital X of 4. And so that would be doing the discrete Fourier transform using the linear transformation. And so the big thing to remember from here is you had your lowercase x of n, and then we got our W4 matrix. Reason why it's capital N equals 4 here is because our x of n is a 4 rows by 1 column matrix. The insides must match, and we know Wn is a symmetrical matrix. So the inside, we know this must be 4 in order to match with this one to perform matrix multiplication. And so this is symmetrical, so it's a 4 by 4. We have it here, and we calculate each one. So W4 is 0. Remember, Wn we define as specifically e to the negative j 2 pi over capital N. But remember, in our numerator, that is what we multiply by here. If you just look back at the original, the n times k, and the n times k is given in the top part here. So that's why we add e to negative j 2 pi over capital N. That's our Wn, but multiplied by, and then what's in the numerator here are 0 and gives you 1. And so that's how we solved for each of these. Then we had our lowercase x of 4. We got this matrix. Then we did matrix multiplication. You do the row multiplied by the column. Then you sum them together. You get into the row multiplied by the column, sum them together. And then the final matrix should be the outer of what you have here. So it should be a 4 by 1 matrix. That's what we got for result. 4 rows by 1 column. So that was our DFT. So that's why it's capital X of 4 using linear transformation. And so that's how we solved for it for that example. Now that we talked about that, we need to talk about the other ways you can do the discrete Fourier transform using the time domain circular convolution and then using the other technique for the DFT, which is just doing basically the equation method. I summarize it as. So there's 2 different techniques, each of them, in order to get a good understanding behind how to perform them. So we're going to get into the circular shift method. So if it asks you specifically for the time domain circular convolution, so that's what we're going to be talking about right now, time domain circular convolution. And when I see this, basically, if we are given 2 choices, so this is where we're going to start out with our sequence. I think it's best to do it for an example because it's sort of hard to, it's given in the equation as this way, x3 of m is equal to n minus 1, the summation from n equals 0 to n minus 1, x1 of n, and then x2 of m minus n, capital N for m equals 0, 1, etc., n minus 1. This would be the circular convolution written in the summation form. But if you are given the 2, and for the example here, I think it's best explained if we just work through it. And it says, perform the circular convolution of the 2 sequences. So for our first sequence, x1 of n is equal to 2, 1, 2, 1. And then we have our x2 of n is equal to 1, 2, 3, 4. Okay. Here, what we notice is this 2 specifically is at index 0. This one is specifically at index 0. So you know, just ahead of time. So this would be n0, n1, n2, n3, n equals 0, n equals 1, n equals 2, n equals 3. So it says perform the circular convolution of the 2 sequences. So the first part, what we're going to realize is when we write this out, we would begin with at m equals 0. And why do I state this specifically is because we have to do the summation and we're going for m equals 0, 1, 2, and then our n, this is length 4. So 4 minus 1, we're going to go up to m equals 3. So we're going to start at m equals 0 and go up to m equals 3. So if we wrote this in equation form for the first circular convolution, it'd be x3 is 0 is going to be equal to, and then it'd be the summation from n equals 0 to n minus 1, x1 of n, and then x2, and then our m would be 0 here, so it'd just be minus n, and then our capital N is 4, the length. And so x3 is 0. When we do this specifically, we're going to get our, when we draw the circle, we have to draw one for x1 of n, and then I'm going to draw one for x2 of n, but then one for x2 of minus n. So here would be, we're going to actually have by the end 4 circles, and you'll see why. So this is my x1 of n circle, and here's my x2 of n a circle. And so x1 is 0. So x1 is 0 is going to be equal to, at 0.0, it's 2 here, right? It's going to be 2. We're going in the counterclockwise direction. So x1 at time step 1 is going to equal 1. x1 at time step 2 is going to equal 2. x1 at time step 3 is going to equal 1. And then my x2 of n, so my x2 of 0 is going to equal 1. My x2 at time step 1 is going to equal 2. x2 at time step 3 is going to be, sorry, at time step 2 is going to be 3. My x2 at time step 3 is going to be 4. Now, in our circular convolution, it's x1 of n, and then multiplied by x2 negative n. We have x2 of n, but we need to x2 of negative n. What you're going to notice for x2 negative n is, notice how we're going originally counterclockwise. We're going to now just draw it going clockwise. So we're going to do the opposite direction. That's what that minus sign is telling us. So we're going to get x2 of 0 is going to equal, and then it's going to be 1. And then down here, we're going to have x2, and then it's going to be x specifically of 1 is going to equal 2 because we're just writing it now going clockwise. X2 of 2 is going to be 3. And then we're going to have x2 of 3 is going to equal 4. Okay. And now we have our x2 of negative n here. And now we need to do the multiplication of the 2. That's what it requires. So it's x1 of n multiplied by x2 of negative n. So at our first point, it's going to be x1 is 0, multiplied by x2 0 is going to be 2 times 1, so it's going to be 2. Then for next point up here, we're going to have 1 times 4, which is 4. Next point over here, it's going to be 2 times 3, 6. And then it's going to be 2 times 1, 2. And now you're going to sum them all together around the circle. It's going to be 2 plus 4 plus 6 plus 2. And so 2 plus 4 plus 6 plus 2 is going to equal, and then that would be 6, 12, 14. So that would be your x3 of 0 is going to equal 14 for the first one. Now, you're going to do at m equals 1. And so at m equals 1, what we're going to see in our equation, it's going to be x3 of 1 is going to equal, then it's going to be from n equals 0 to n, capital N minus 1, x1 of n, x2, and then it's going to be 1 minus n to the 4, because the m is now 1, so within here, it's now 1, and so it's going to be 1 minus n, and then what we're going to see within our circle is what do we have to do differently this time? So I'm going to have my x1 of n circle. I'm going to have my x2 of 1 minus n, and then we're going to have our final. So this will be where we have the result. So for my x1 of n, everything stays the same. So at time step 0, it's 2. At time step 1, it's 1. At time step 2, it's 2. And at time step 3, it's 1. Okay? But here for your x2 of 1 minus n, you're going to notice that you're going to shift everything downwards. So see this original one, x2 of negative n, you're going to shift everything over in that direction. So shift, 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 shift. And so that's going to make this spot now become 2, this spot now become 1, this spot now become 4, and this spot here come 3. And now when you do your x1 of n multiplied by your x2 of 1 minus n, you're going to get as your result, 2 times 2 is 4, 1 times 1 is 1, 2 times 4 is 8, 1 times 3 is 3. And now you're going to add them all together. So x3 at time step 1, because your m equals 1 here, is going to equal 4 plus 1 plus 8 plus 3. When you go around that circle, add them together, 5 plus, and then here you're going to get 11. That will give you 16. Okay? And then when you do your at m equals 2, what you're going to notice specifically within it, you're going to have your circles again. The thing is, you'll just shift it over one more time. And so you're going to get specifically your x1 of n remains the same. No shifting is done on that one. So it's 2, 1, 2, 1. Your x2 of 2 minus n is going to be you shift over 2 instead of just 1 from the original x2 negative n, you'd shift over 2. So this spot would actually end up over here, the spot on the other side. And then that's what you do is you'd shift twice. So it's going to be 3. And then it's going to be 2, 1, 4. And then your x1 of n, x2 of 2 minus n, it's going to be 6, it's going to be 2, it's going to be 2, and it's going to be 4. Add them all together, you're going to get x3 of 2, which is going to be your 6 plus 2 plus 2 plus 4. It's going to be 14. And then when you do at m equals 3, what your result's going to be for x3 of 3, doing the exact same thing, you just shift now by 3 from the original up here, and you're going to get the result of 16. So in the end, your vector, which is going to be noted as specifically the capital, because this was for finding the DFT, sorry, and then you perform the inverse DFT. So what you would actually get here for your vector, for your x3 vector of n, from your results, the first index was at 14. So you would bold that one because that starts at index 0. And then you would get 16 for index 1. At index 2, we saw 14. And then when you solve for index 3, you'll get 16. And that would be your result, specifically how you did that time domain circular convolution of the two sequences in order to get your x3 of n, your results. And so that is obtained with the circular convolution you got. And so that would be the answer using the time domain circular convolution technique. Okay, so that is the whole process that we had from the beginning to end. And then I want to use the exact same wording as the book in sense of the next technique. They call it, let me look here. Okay, they say for the next one, they would say instead of the time domain circular convolution, they would say for this one, use the 4-point DFT and IDFT to calculate your result for x of n. And so this one will be a little more complicated of a process because you have to use more of the formulas. So the formulas that are provided specifically are the ones that we wrote down beforehand. And so when you remember, when we're dealing with the discrete time Fourier, the discrete Fourier transform, and then we're going to go into the inverse discrete Fourier transform to produce back our result, we first have to use the DFT. That's what's telling us. We have to do 4-point DFT, and then we have to calculate the IDFT. And so then we have to do the inverse of it. So we're going to go and we're going to get our capital X of K, and then we're going to take the inverse discrete Fourier transform to produce the answer in little x of n. And so this process is just a little more lengthy, so you guys know. And so what we're going to do for this one, we're going to use the sequence for x1 of n is equal to 2. And so this is at index 0, 1, 2, 1. And then we're going to have x2 of n is going to be from 1, 2, 3, 4. Okay. And so what we're going to see from here is these are both length 4, correct? So we're going to make our capital N we know is equal to 4. That's what we know because capital N represents the length of your sequence, and the length of both sequences is 4. So to do the 4-point DFT, what we're going to see is we're going to calculate the 4-point DFT of x1 of n first, and then we're going to calculate the 4-point DFT of x2 of n. And so when we do the 4-point DFT of x1, it's going to be x1, and it's going to be capital K. And then remember from your discrete Fourier transform, when you do it, that's what I'm just copying from here. So our x1 of capital K, then we're going to have our x1 of n, and then we're going to plug it into this equation. So it's going to be the summation from, and then remember, n minus 1, because capital N's 4, 4 minus 1 is 3. It's going to start at n equals 0. And then it's going to be our x1 of n. That's what we're plugging in. And then it's going to be e to the negative j 2 pi k of n all over capital N, which is 4. And then this is going to be for k equals, remember, it's 0, 1, 2, all the way to n minus 1, which would be 4 minus 1, which is 3. So 0, 1, 2, 3. That's where we stopped at. And so here we can tell specifically when we go x1 of 0, that's going to be 2. So it's going to be 2e to the power of, and then it's going to be, this would be 0. So e to the 0 is 1, so it's just going to be 2. And then for our next one, we're going to plug in x1 at position 1. So at position n equals 1, it's going to be 1 e to the negative j 2 pi, and then it would be k over 4, which would be e to negative j pi k over 2. And so that's why we get plus e to the negative j, and then it's going to be pi k over 2. Then when you plug in x1 at position 2, you're going to get plus 2e to the e negative j 2 pi, and then we're going to be at position 2, so 4 all over 4. That would be e to the negative j pi k. And then your x1 at position 3, it's going to be 1 times e to the negative, and then plugging in here, it would be e to negative j, and then 6 pi over 4, which would be e to negative j 3 pi k over 2. So that is for all of ours. So what we're going to see here is this is our x1 of k, but remember, k runs from 0 to 3, so we need to plug in k equals 0. What do we get as our result? K equals 1, k equals 2. So x1 of 0 is going to give us 2 plus e to the 0 is 1, plus 2 e to the 0 is 1, plus e to the 0 is 1. And so it will be 2 plus, and then 4, so we get 6. It would just be 2 plus 1 plus, then 2 plus 1, which is 6. X 1, 2, 1. When we plug in k equals 1 here, we're going to get 2 plus e to the negative j pi over 2 plus 2e to the negative j pi, and then plus e to the negative j 3 pi over 2. So here, what we're going to notice is you need to write these in terms of cosines and sines. So this is actually going to be 2 plus cosine, and then pi over 2, and then minus j sine pi over 2, plus 2e, and this is going to be, sorry, cosine, and then it's going to be of, and then pi, minus j sine of pi. And then here we're going to get plus cosine of 3 pi over 2 minus j sine of 3 pi over 2. Okay, now that we got that, what we're going to have here is this is going to be 2 plus, this goes to 0, so it's just going to be minus j. And then here we're going to get, this goes to 0, sine of pi 0, 2 times negative 1, so it's going to be minus 2. And then here we're going to get cosine of 3 pi over 2 is 0, but this would give us negative 1, so be actually plus j. And so what we're going to get is 0 for our x1 of 1. And then when you plug in x1, when you plug in k equals 2, you're going to get 2. When you do x1, you plug in k equals 3, you're going to get 0. And so that's the thing. Let me see. How did we get the 2? Oh, okay, you answered it, Kato. Okay. Now that we talked about that, we basically went through and we got our x1 of k. So we found the 4-point DFT of x1 of n, but now we need to find the 4-point DFT of x2 of n. And so doing the 4-point DFT of x2 of n, you're going to get x2 of k is going to equal, and then remember, this length is 4 for your x2, n equals 4. So it's going to be 3, and then because it's n minus 1, 4 minus 1 is 3, n equals 0, then it's going to be x2 of n, and then e to the negative j 2 pi k n all over 4. And your k is going to run from 0, 1, 2, all the way up to 3 because it's n minus 1, capital N minus 1. Now that we got that, what we need to do specifically is same exact process here. When we have our, we're going to find our n ones first, and we're going to plug in our k's afterwards. So plugging in x2 for n equals 0, n is 0 for your x2 of n is at 1, the value. So it's going to be 1 e to the 0, which is just 1, plus. And then the next one, x2 at position 1 is going to be 2. E to the, and then it's going to be negative j 2 pi k n all over 4. So that's just e to the negative j, and then it's going to be pi k over 2. Then it's going to be plus, and then when you plug in x2, position 2, it's going to be 3 e, and then you're going to get negative j pi k, and then plus 4e to the negative j 3 pi k over 2. Okay, now that we got all of those, we do the exact same process. So this is our x2 of k. Now we need to solve for x2 when k is 0, which is going to be when we plug in k equals 0, you're going to get 1 plus 2e to the power 0 is 2, plus 3e power 0 is 3, plus 4e power 0 is 4. This is going to be 7, 9, 10. Okay. Let me see. 7, 9, 10. Yeah. Okay. Now we need to go x2, plug in 1 for k. You're going to do that. And once you do that and you write it in terms of cosines and sines like we had up here, simplifying it, you can go back and check this. You should get negative 2 plus j2. x2 of 2 is equal to negative 2. And x2, when you plug in k equals 3, you're going to get negative 2 minus j2. Okay. And so now we have our x1 of k vector and our x2 of k vector. And so what we need to do is our x3 of k is going to equal the multiplication of the 2-point DFTs. And so we're going to have, it's going to equal our x1 of k times your x2 of k. And remember, from up here, our x1 of k we determined was going to equal, and the vector was going to be 6 at time step 0, then it was at time step 1, 0, time step 2, 2, time step 3, 0. Your x2 of k is going to equal, and then your vector is going to be 10, and then negative 2 plus j2, negative 2, and then negative 2 minus j2. Doing the multiplication of the 2, you're going to get here 60 in your first position. Then you're going to do 0 times this, which would be 0. 0 times anything is 0. 2 times negative 2 is negative 4. Then 0 multiplied by this is going to give you 0. Okay, so that's going to be your entire vector for your x3 of k. Now you do the inverse. So when you do the inverse, because now we calculated this is exactly the 4-point DFT right here. This is our 4-point DFT, our x3k, because it's the multiplication of the x1 of k and the x2 of k. The 4-point DFTs are the individual ones that give you the total 4-point DFT. Now we need to do the inverse, so the IDFT of our x3 of k. And so in order to perform the inverse operation on this, so the IDFT, remember, from our formula we went over earlier, let me see, here it is. Your x of n, the IDFT is equal to 1 over n, our n is 4, and then 0 to 3, x of k e to the j 2 pi k n all over 4. And so that's what we're going to be using here. And so when we have our x3 of n is going to be equal to, looking at my formula, I'm going to write it's 1 over 4, because capital N equals 4. And then it's going to be 3 from n equals 0 all the way up to 3. And then it's going to be, oh wait, IDFT. Let me make sure I wrote that. It's k equals 0. Sorry, I think on my IDFT here, just make sure you have k, not n. Sorry, because it's k you're doing from, and so up here it was n equals 0, here is k equals 0. Just make sure you fix that in case. It's just in the summation. I don't think it should be a big issue. Here we need to do then our x3 of k, that vector we found, times, and then it's going to be e, and then what we're going to have here is j 2 pi and then Kn all over capital N, which was determined as 4. And then it's going to be for n equals 0, 1, 2, and then n minus 1 is 3. And so that would be our IDFT. And what's going to happen now is we basically are going to have to plug in specifically for our k equals 0, our k, what we have here is our x3k when it is 0, it is 60, and then we'll go through it. So let's look at each of these in order to perform this x3 event and get the results. It's going to be here 1/4 on the outside, then on the inside it's the summation. So at x3 0 it's 60, and then it's going to be e, and then this would be 0 is 1, of course, because e to the power 0. So when our k equals 0, it's going to be 60. And then when the next one, it's going to be 0, so plus 0. So 0 times anything be 0. The next one is going to be -4. And then this would be e to the, and then we're going to have j. So this would be 4 pi k all over 4, which would just be pi k. And so here, sorry, pi n, because we're plugging in for k. That's a big thing. Notice that here we're doing the summation of k. And so we're going to get -4 e to the j, and then this would be pi n. Because we plug in for k equals 2, that would be 4 pi over 4, so that's what we get, pi. And then our last one would be plus 0. Okay. Now we got 1/4, and then it's going to be 60 minus 4e to the j pi n. This can be simplified to 15 minus, and then e to the j pi n. Okay, now that we got that, we need to solve for x3 of 0, which is plugging in 0 here. You're going to get 15, minus 1, which is going to be 14. Then you're going to have x3 of 1, which is going to be your plugging in for 1 here. You're going to get 15 minus e to the j pi, which you can write as 15 minus, and then isn't this cosine of pi plus, and then j sine of pi? This term will go to 0, where this term will be -1. And so 15 minus a -1 will be +1, so it would be 16. Then your x3 of 2, it's going to be, here you're going to do the exact same math. You're going to get 14 though, and then your x3 of 3, you're finally going to get 16. So for your x3 of n vector, at the end result, you're going to get 14, 16, 14, 16. Remember, the first one starts at index 0, and then that would be your same result. It takes a long time, though, you can tell. The main thing when you have to calculate the 4-point DFT and IDFT is when you start out, when it asks you, you have to do the 4-point DFT of the first sequence, you have to do the 4-point DFT of the second sequence, and when you do those, first you plug in, because your summation is running from n0 to n3, you plug in n first, then you plug in k. And then here, your summation, you do whatever your summation's running from first, then you plug in your k. So we got the 4-point DFT is the multiplication of the two sequences, their DFT, so x1 of k multiplied by x2 k, so we got the final x3 of k here. And now that we got that, then we use the IDFT, so the discrete for, or sorry, the inverse discrete Fourier transform. The inverse discrete Fourier transform, we looked at our equation. Remember, it runs from k equals 0 to 3. That was the one correction we had to make here, from k equals 0 all the way up to n minus 1, where capital N was 4 in this example, so that's why it's 3. Then x3k, and then we plugged in here for capital N4. So first you do the summation of the k's, and then you plug in the n values, n0, n1, n2, n3. Then you get your x3 then. So that was the entire process of doing the DFT and IDFT in order to get a good understanding behind it. Okay, now that we talked about that, the big thing that we'll focus on is the examples in the last homework. And so which of those, when looking at it, going back to it now, let's see, is there anything we should be aware of? Okay. There are a few properties I want to highlight in there because I think they're important in order to do well. So we did the circular and we did the DFT and IDFT. So I want to do the other ones that might possibly pop up, so you're familiar with all types. So now we're going to be given the two sequences. So for example, for the sequences, x1 of n equals cosine 2 pi over capital N lowercase n, x2 of n equals sine 2 pi over capital N lowercase n for 0 n to n minus 1. Okay, so what this one says is determine the n point circular convolution. Okay, so they didn't say use the time domain or anything. They just gave us the circular convolution x1. Circular convolutions written this way, where it's the convolution, but they just put a circle around it, the operator. Then x2 of n. So they said determine the endpoint circular convolution. And what we need to do from this is we need to write our cosine and our sine terms, our x1 and our x2 in terms of exponentials. So if we wrote x1 of n in terms of its exponential format, we would get e to the j 2 pi n over capital N. And then we're going to get plus e to the negative j 2 pi n all over capital N. And then for our x2 of n, we're going to get 1 over 2j. And it's going to be e to the j 2 pi n all over capital N minus e to negative j 2 pi n all over capital N. Okay, so that is because this is cosine. We just written it in terms of the exponential form, and then we wrote the sine in terms of the exponential form. So it said determine the endpoint convolution circular, determine the endpoint circular convolution. So when you saw that endpoint, you're probably thinking, oh, this is the formula-based one. And so using the DFT and IDFT. And so our x1 of k, if we're doing this in the summation, it runs from n equals 0 to n minus 1, x1 of n, e to the negative j 2 pi k lowercase n all over capital N for k equal to 0, 1, and then all the way up to n minus 1. That's literally just from the formula there for the DFT. So I'll just put that the DFT formula, discrete Fourier transform. And what we do is we notice here, we're going to plug in for x1 of n what we have here. And so we're going to get as our result, it's going to be 1/2. I'm just going to take that out of the summation because that's a constant. And it's going to run from n equals 0 to n minus 1. Plugging in now here, we have e to the j 2 pi n all over capital N for the first part, multiplied by e to the negative j 2 pi k n all over capital N. Then I'm going to just split this up. So I'm going to do the first one, the second term. I take the 1/2 out, the coefficient. It's going to be n minus 1, n equals 0, e to the negative j pi 2 pi n all over capital N multiplied by e to negative j 2 pi k n all over capital N. Okay, now we got the two written out, but what we have to do is we have to put this in a particular format so that we can use a specific property, which I'll go over. So here, we're going to combine the two exponentials. We're going to simplify this part of the equation. So it's going to be e, and then we're going to have negative j 2 pi n all over n, then it would be k minus 1. And then here we would have plus 1/2, then n equals 0 to capital N minus 1. We get e to the negative and then j 2 pi n all over capital N. Then it would be our k plus 1. Okay, that's just simplifying. All I'm doing is simplifying here, writing it in terms of one exponential, not two multiplied by each other. I just simplified and combined the two. And now, what's an important property that he didn't cover in his lecture notes, but you should have written down? Let me put it here on the side. If you have your x of k is equal to the summation from n equals 0 to n minus 1, e to the negative j 2 pi n all over capital N, k minus k0, where k0 is just a constant, it's going to be equal to capital N delta, and then this is k minus k0. Okay. And so what we have here is we wrote it in this format where we had negative e to the negative j 2 pi n over capital N, k minus, and then k0, where k0 is a constant, which is 1. So this is going to equal, and then so we have 1/2, then we'll replace this entire summation with what we have here. It's going to be n and then delta k minus 1. And then here it's going to be 1/2. Then it's going to be n delta k plus 1. Okay. Now we're going to combine the two. So we're going to get the simplified result. And our simplified result for this one would be n over 2. And then it's going to be delta k minus 1 plus delta k plus 1. Okay. So that's for your x1 of k. The big thing here is we took our x1 of k, our x1 of n, we wrote it in terms of complex exponential terms. From the cosine, we used the trig identity, so we wrote it in exponential terms. Then we found our x1 of k, and then using our x1 of k, we wrote it in terms of the summation here, because we knew that summation is equal to capital N delta k minus k0, where k0 is a constant. So we wrote the k0, so we got the constant over here, and we're able to apply that definition. Okay, we found the x1 of k. Now we need to find the x2 of k. The x2 of k. Now our x2 of k is going to be equal to, and this is the exact same technique we have. It's n minus 1, the summation from n equals 0 to n minus 1, x2 of n, and then e to the negative j 2 pi k n all over capital N for k equals 0, 1, 2, all the way up to n minus 1. Okay. And we wrote it x2 of n in terms of complex exponentials. So that's what we had over here. And I'm going to split it up into two different summations, one for this term, one for the other term. And so I'm going to get my 1 over 2j. That's a constant, which I just bring out the summation. And then from n equals 0 to n minus 1. And then it's going to be e, let's see. Yeah, I would just get my e to the j 2 pi n all over capital N multiplied by e to the negative j 2 pi k n all over capital N. And then plus, and then the other one, which is going to be, oh wait, this one is going to be my minus, sorry, on this side, because remember sign, there's a minus sign between we had here, so the minus e to negative, so that one's going to be minus, then it's going to be the summation here. Oh, the 1 over 2j term comes out in front, remember, so summation from n equals 0 to capital N minus 1, e. And then here we have the negative j 2 pi n all over capital N e to the, and then this would be negative j 2 pi k n all over capital N. And then here, what we're going to have is we know this summation. Let's write it in terms of one exponential. So we'll combine the two until we get n equals 0 to n minus 1. Then we're going to have e to the negative j 2 pi, and then it's going to be k minus 1 all over capital N, and then minus 1 over 2j, n equals 0 to n minus 1, and then it's going to be e to the negative j, and then it's going to be 2 pi, and then it's going to be k plus 1 all over n. Okay, now we got the 2. What we have to do with this is, remember, this summation here can be written as n delta k minus k0. So this is going to be written as n delta k minus 1. Then this is going to be written as n delta k plus 1. Okay. So then we're going to now simplify. So we're going to get n over 2j multiplied by delta k minus 1 minus delta k plus 1. Okay. That's our x1 and our x2 of k. That's our x2 of k. So now our x3 of k is going to equal the multiplication of the 2. The convolution turns into multiplication. Remember that in the once you take the Fourier transform. So we're going to get our x1 of k, remember, was n over 2. Then it was delta k plus, minus 1. And then it's going to be plus delta k plus 1. And then multiplied by n over 2j. And then we're going to have delta k minus 1 minus delta k plus 1. So what you're going to do after you do the multiplication of the 2, the end result is going to be n squared all over 4j. Then you're going to get delta k minus 1 minus delta k plus 1. Okay, you get that as your result. Now, the big thing to see here is that you're going to get, you can rewrite this as the following. Isn't this the exact same thing? Delta k minus 1 minus delta k plus 1. And what you'll notice is that this part right here is equivalent to what you got for your x2 of k here. And so you can write n2 times x2 of k is your result of that convolution. And when you have to do now your x3 of n, remember, this is just a constant. N is just a constant. So it's going to be n over 2. And then we know what x2 of n was in the beginning. x2 of n was given to us. So it's just going to be sine, and then this would be 2 pi over n times n. Because we know what, when we take the inverse IDFT, the inverse of x2, capital X2k, the x2 of n is sine 2 pi n over n. And so that's how we got our answer. Okay, I know that was a long one for the circular convolution, but I think it does a really good job explaining how that works. And then the next ones are going to be pretty fast ones, I feel like. So hopefully this one was longer, I know, but it was good to understand it, how those two worked, applying that to an actual proof in case he gives you that. Okay, so for our next example, we're going to be doing the following, where we're going to have compute that. Okay, so for this example, it's going to say compute the endpoint DFTs of the signals. Your first signal's x of n is equal to delta n. So remember, when we do the DFT, it's just asking for the DFT. Your x1 of k is going to equal from n equals 0 to capital N minus 1. Then you plug in for your x of n, which is delta n here, e to the negative j 2 pi, and then it's going to be k n all over capital N. I just plugged in for my x1 of n, delta n. And so here, what we're going to do is, remember this runs from k equals 0, 1, 2, all the way up to n minus 1. So we're going to remember the delta function. If you multiply it by something else, it's just this value only occurs at what the delta function occurs at, and the delta function occurs at 0. So it's going to be e plugging in here. It's going to be e to the 0 for your n. So what you're going to get as a result is your delta n multiplied by e to the negative j 2 pi k times 0 all over n. N equals 0, n minus 1. And what this is going to give you is e to 0 is 1, correct? And so you're just going to get 1, basically. And then, so the summation from n equals 0, n minus 1 of delta n, well, this one only occurs at step 0, so the entire summation is just going to equal 1. Because the delta function only occurs at 0, everywhere else it's 0, so the entire summation would just equal 1. And then here, for the next one, for part B, if they give you x2 of n is equal to delta n minus n0, where 0, it's between n0 is between 0 and capital N, your x2 of k it's going to equal n minus 1 all the way up from n equals 0, n minus 1. It's going to be delta n minus n0 e to the negative j 2 pi all over capital N k n. And so what we're going to notice is, remember the delta function, you just plug in where it occurs due to the rule, the delta function, we've seen this in 310. You plug in where the delta function occurs into the other function. And so we're going to get delta n minus n0, and then e to the negative j 2 pi all over capital N k, and then n0 is what you plug in. And so what you're going to notice is what we're going to see here is this will only occur at n0, correct? The delta function. Everywhere else it's going to be 0. So it's going to be 0 multiplied by this. So at the end result, it's only going to occur at n equals n0, and n0 is between 0 to n, so it will occur. So that's why we're going to see it's going to be equal to e to the negative j 2 pi k over n times n0, because n0 is bounded between 0 and capital N, so it will occur in the summation. So this will be 1 at time step n equals n0. So that's why our final result is e to the negative j 2 pi k over capital N times n0, because it only occurs at that one time stop. And then for the next one, for part C, when it's x3 of n is equal to alpha n for 0, n, and then capital N, what we're going to see for x3 of k, it's going to equal n minus 1 from n equals 0, alpha, and then n, that's what we're plugging in here. Then it's e to the negative j 2 pi all over capital N k n. This is going to be, what we're going to see is, can't you write this summation, n minus 1, n equals 0, and then take out the n as the common, so alpha, e negative j 2 pi all over capital N times k all to the power of n. What we're going to see here is, doesn't this remind you of a geometric series, which we had here, where we have from n equals 0 to n, capital N minus 1, then we have alpha n, because this will just refer, a to the power of n will refer to this whole thing as our a to the power of n, and then it's from n equals 0 to n minus 1. And then that is equal to 1 minus a to the power of n all over 1 minus a. Okay. And so our a here is this entire thing. So it's going to be 1 minus, and then it's going to be alpha e to the negative j 2 pi over capital N times k. So that's our a. And then raised to the power of capital N all over, and then it's going to be 1 minus alpha. So 1 minus, 1 minus a, which a is alpha, e to negative j 2 pi all over n k. Okay, now we got that in. Now what we're doing is we're going to see as a result of this is that this term will cancel this one, the ends. And we're going to get 1 minus alpha e to negative j 2 pi all over n times k. And then in our numerator, what you're going to see is this term here, e to the negative j 2 pi k. K is equal to 0, 1, 2. And isn't e to the negative j 2 pi, that's always going to land on the unit circle at the same exact location, because negative 2 pi on the unit circle, if you draw it, if you go around negative 2 pi, you're always at 0, that 0 point again. So it's going to be 1. So this e to negative j 2 pi k is going to equal 1. So it's going to be 1 minus alpha times 1. So your final result will be, you're going to have your 1 minus alpha, and then it's going to be all over 1 minus alpha e to negative j 2 pi k all over n. Then for part D, you're going to have your x of n is going to equal e to the j 2 pi all over capital N k0 n. And so what we're going to do is it's between the two. So what we're going to do is when we write our x of k is going to equal the summation from n equals 0 to n minus 1. And then we're going to have x of n e to the negative j 2 pi k all over capital N. What we're going to see as a result is we're going to have n minus 1 to n equals 0. And it's going to be e to the j 2 pi, what we're substituting in for x of n, and then k0 n e to negative j 2 pi k all over n. And this is going to equal what we're going to see as a result is we'll write this in terms of one exponential, so n equals 0 to n minus 1. And so right in terms of one exponential, we're going to have e. And then it's going to be negative j 2 pi all over n. And then combining, so you're going to get k minus k0. And recall k0, this would be n. Oh yeah, I just forgot to put in here e negative j 2 pi. My n, sorry, got covered out. And so this would be multiplied by n here. Okay, now this reminds you of what we had before, where when we had it written in the sequence, we can rewrite it as n delta, and then it's going to be k minus k0. So that's our answer. So those were the 4 different techniques we had in order to simplify specifically what we got and get the result. Okay,
I have a
so
question for this problem.
yeah.
Uh, I can't really see because okay, wait. Uh,
Um,
maybe you just forgot to write an N somewhere. It was I
this
think
one,
for part. Could you go to your part B?
this one. Oops.
Yep, perfect. Uh, okay, never mind. I just wrote something wrong.
Okay,
Continue on.
cool. Okay, and then our last example will be focusing on the 10-point inverse DFT. And so we're going to apply a few properties I want to make sure you guys have written down just before the exam. So the last one here, let me zoom back out. Okay. And so it's going to say, for this example, you need to find the 10-point inverse DFT of, then you have your x of k. It's going to equal 3 for k equals 0, and it's going to be 1 for 1 through 9. Okay. So for this one, what we have to do is our x of k, if we write it in terms of specifically the delta function, what we're going to notice, so we want to write it in terms from 0 to 9. Okay, so what we're going to have is it's definitely 1 plus, and then we're going to say 2 delta k, because our x of k occurs, it's 1 from 0 to 9. It's definitely has the value of 1, but it's an additional plus 2 at k equals 0. So only at time step 0, which is at k minus 0 in here, it's time step 0, it's going to add a 2. But otherwise, it's just 1. So at time step 1, it's just 1 because this is 0. And so now that we know that, there's a few properties I want you guys to have written down. So this will be your x of n, and this will be your x of k. And this is your DFT properties. Just to make sure you have these on your cheat sheet. If not, so if you have delta n, it's going to be 1. If you have 1 over here, it's going to be n delta k. And the big one that I was telling you guys, it's not in the properties table. It's not like a 1-to-1 where you can go from one to the other. Is from here you can go between the two, but make sure you had written down when your x of k is equal to, and then the summation from n equals 0 to n minus 1 e to negative j 2 pi n all over capital N k minus k0. That is the same thing as n delta k minus k0. You can simplify it. So these are big properties. Make sure you know. And then this was another one which I talked about in the DFT. When you're working with it, one that commonly pops up, that you can simplify this summation to this result. So for the DFT properties, what we're going to apply here is we have to go from the x of k to find the x of n. And so from this x of k of 1, well, what we see from 1 is it's just delta n. So that one was easy. We got that part of the equation. But 2 delta k, here, what is our capital N? Well, our capital N is the length of our x of k, and the length of our 1 is this one, right? Because remember when you do, you start from 0 and you go to n minus 1. So our capital N must equal 10. So we have 10 delta k. So over here, this would be, if we have a 10 in front here, it'd be 1 divided by 10 multiplied by 2 in front. So 2 times 1 over 10, that's going to be 1 over 5 plus delta n for your x of n. Because the delta n came from the 1, which was straight from the table. But here, when we had a delta k, it was 10 for the length of ours. So then you have to divide it. You do 1 over 10. And because you divide the 10 over on this side, and then you multiply by 2. And so that is pretty much everything. The reason we divide by 10s over here, because we have to take into account how many of them there are. So you can write as 1 over n is equal to delta k, if that is easier to understand. 1 over n is equal to delta k, because you have it here and then you just multiply by 2 in front because that's the constant that kept the same. But that would be your final answer and results. And let me see real quick. Any way you can do number 1 as well. Phil, what do you mean by that? I thought I did number 1.
Or just like the homework on the homework question for number 6. Oh,
I
shit.
did that one.
Okay. Yeah, my bad.
Okay. And I think that will conclude everything for this class. So let me stop the recording.